Hello, I'm Max Argos, and I will present Contrastive Representation Learning for Hand Shape Estimation, which is joint work together with Christian and Thomas that was conducted at the University of Freiburg in Germany. This is the outline for my talk. First, I want to introduce the problem of hand shape estimation and motivate its importance. Second, I will review some of the state-of-the-art approaches and compare them to our work. Then I'll introduce HanCo, which is the dataset we use for our experiments. Finally, I'll talk about our approach and discuss the experiments conducted. But first, let me introduce the task. We are working on the problem of hand shape estimation, which means that given a single RGBD image, we aim to estimate parameters of a hand shape model. These parameters describe articulation and shape of the hand, as well as its global rotation and translation in space. Hand shape estimation is useful because from the parametric representation, hand pose can be easily derived. Understanding of hand poses is useful in robotics as well as for gesture control of human-computer interfaces. Let's quickly look into related approaches on hand shape estimation. Most approaches learn a direct mapping from images to some hand scene representation. In order to learn this function, large amounts of labeled images are needed. Obtaining these annotations is difficult because it is not easily solvable through crowdsourcing of annotations. Ideally, we would like to alleviate the need for annotated images by making use of unlabeled data. For other tasks, approaches were presented that can learn meaningful representations from datasets of unlabeled images. These often formulate pretext tasks, and recently contrastive approaches have become popular. They have allowed researchers to achieve the same accuracy using less labeled data, or to outperform ImageNet-based pretraining, which is the current gold standard in hand shape estimation. Our work aims to bring these advances into hand shape estimation, and to this end, we have collected and publicly released the HanCo dataset. The dataset was recorded with the setup depicted. We have recorded about 100,000 time instances with 8 RGBD cameras, giving us a dataset of around 860,000 images, of which approximately 7% have been labeled. Our dataset has the following unique properties: a green screen background allowing for simple background randomization, having intrinsically and extrinsically calibrated cameras, and short video clips of hand motion, as well as showing a variety of hand-object interactions. Here we see some example images from our dataset. From left to right, it shows one unique aspect of our data collection: the possibility to replace the background with a new one, sequences of hand motion, and finally, the same hand pose being observed from different viewpoints. Contrastive learning is based on image pairs. We can have positive pairs showing the same thing and negative pairs showing different things. With these, a neural network is used to calculate embeddings for images. Two embeddings, Q and K, are compared with each other using a cosine similarity. Training maximizes the similarity of positive pairs and minimizes that of negative pairs. The question remains, how do you generate pairs of similar images? And this is exactly where our contribution lies. The most commonly used way to generate positive samples for contrastive learning is to rely on image augmentations. A reference image is passed through an augmentation function twice to generate a positive pair. The HanCo dataset yields more ways in which positive samples can be generated. First, we use background randomization, which leverages the green screen background to generate positive samples. Each two of the 3 images shown could be used as positive pairs. Second, sampling temporally adjacent frames of a sequence is possible. We call this temporal sampling. We combine this with background randomization. Here, note how hand pose slowly changes between frames. Lastly, we can leverage the multi-camera setting by sampling positive pairs of different views from the same point in time. Again, we combine this with background randomization. Overall, our method is a two-step process. First, we pre-train our encoder backbone, extending the MoCo method by He et al. With one of our image sampling strategies. Second, we transfer the encoder weights and do supervised training of hand shape estimation, as is done in Zimmermann et al. Let's look at some of the results. We report results for 3 previously used metrics for hand shape estimation. Mesh error is the Euclidean distance between corresponding mesh vertices of ground truth and prediction. This should ideally be 0. F-score is the harmonic mean of precision and recall for a given distance threshold. This should ideally be 1. We compare variants of our approach with 3 published approaches. Our approaches are identical to the one by Zimmermann et al., except for the network initialization. Zimmermann et al. Uses ImageNet weights as initialization, and we use our pre-trained ones. Just following the approach of He et al. And using only image augmentation techniques does not outperform the ImageNet initialization used by Zimmermann et al. When we use background randomization during pre-training, results improve substantially over the baseline. While the improvement in mesh error is only 0.5 millimeters, we see an improvement of about 2% on F-score at 5 millimeters compared to Zimmermann et al. Surprisingly, including temporal neighbors in the sampling process does not further improve results over background randomization. On the other hand, sampling images across multiple views allows us to improve results over background randomization. There's an improvement of 3.6% in the F-score at 5 millimeters over the baseline. Qualitatively comparing our results to Zimmermann et al., we can see that the differences are sometimes visually subtle, but generally hand articulation is captured more accurately. We can see this in the general hand shape, here as well as here, and the position of the small fingers, which are improved here as well as here, for example. By feeding manually picked images into the embedding, we can analyze the representations learned during unsupervised pre-training. We show pairs of images and the resulting cosine similarity scores of their embeddings. The first row shows hand images with different backgrounds, leading to a score of 1. The second row shows similar hand poses, also leading to high scores. The third row shows changes in viewpoints, also leading to high scores. In the last row, we can see that different hand poses lead to low scores despite having the same background. We have presented HanCo, a structured image dataset that allows pre-training models for hand shape estimation. Background randomization and multi-view sampling are powerful strategies for generating positive image pairs during contrastive learning. We are able to outperform ImageNet-based pre-training, and a thorough analysis on the MoCo learned representations was provided. Thank you for your attention.